Welcome. This is the third in a series of presentations designed to provide guidance on specific technical aspects of the indicator methodology. In this session, we look at issues surrounding monitoring and reporting for groundwater. This proved challenging for many countries during the first global data drive of 2017. This presentation is based on an accompanying technical guidance document that was produced by John Chilton, formerly Executive Manager of the International Association of Hydrogeologists. This presentation is a summary of this in-depth document, and for more information it's suggested that viewers refer back to this document. So this presentation is aimed at practitioners seeking further clarification on how to implement the indicator methodology in their country. This presentation discusses why groundwater is more difficult to monitor, and provides guidance on identifying aquifers and how to define bodies of groundwater, reviews options for groundwater sampling, and discusses parameter choice, and it briefly looks at field operations, the suitability of different water quality parameters, and looks at target setting for groundwater. The monitoring data collected for SDG Indicator 632 should provide sufficient information about ambient water quality status and allow long-term trends to be identified. This requires data for the core parameter groups from sites across the country and measurements to be taken in a standardized and consistent way. During the first global data drive of 2017, fewer countries reported on the quality of groundwater than they did for surface waters. This is no surprise and has been a common and consistent feature of such activities in the past. This presentation explores why that should be and recommends how groundwater monitoring programs can be strengthened to provide better information on ambient water quality and how reporting for groundwater can be made more robust and comparable. There are many reasons why water quality monitoring programs do not provide the information they should. This is true for both surface water and groundwater monitoring programs. Further guidance on this topic is covered in the first of the technical documents and presentations in this series. To avoid these failures, information needs and objectives need to be clearly defined. The physical network design needs to be adequately accounted for. Sample collection, handling, storage and analysis must be well planned. Quality control and assurance must be included. Management and interpretation of the resulting data must be understood. Review, feedback and modification of the design must be undertaken. The challenge of groundwater quality monitoring is fundamentally different from that for rivers and lakes. River monitoring can provide a composite picture for an extensive catchment, buffering out the effect of factors local to the sampling station. The reverse is generally true for groundwater, for which the influence of very local factors such as wellhead contamination, well depths, pumping rates, the immediate catchment and sampling protocols can dominate. This can distort the broader picture of groundwater quality for the aquifer and needs to be understood and taken into account. For groundwater, the general constraints outlined above are often supplemented by a lack of hydrogeological knowledge, and this can weaken the design of the monitoring network and also the interpretation of results. This is important because aquifers and the groundwater bodies they contain are usually more complex. The surface waters are much less accessible for sampling. Most groundwaters have longer residence times than surface waters, and this allows time for the physicochemical interactions to take place between the slow-moving groundwater and the material forming the aquifer, and the chemical composition of the water can change as it flows. From a monitoring point of view, the slow movement means that, in general, groundwaters need to be sampled less frequently than surface waters, but obtaining a representative picture of groundwater quality may require a greater density of sampling. The depth and subsurface complexity of aquifers has a major bearing on the choice of sampling point for the groundwater network and the interpretation of the results obtained. samples taken from wells in close proximity can produce very different results, especially if they draw water from different depths in the same aquifer or even from different aquifers. In this next section, we look at how to identify aquifers and how to define groundwater bodies. The first two steps of the indicator methodology are to establish the RBDs, the reporting basin districts, which are based on river basins, and to define the water bodies within them. For groundwater, once the RBDs have been defined, this means identifying the location of the productive aquifers within each RBD and look to see how they might be subdivided into groundwater bodies. As for surface waters, groundwater bodies form the discrete units which are classified as either good or not good. And to monitor groundwater, it is essential to understand the nature of groundwater flow systems, where the water comes from and where it goes to. Simple conceptual hydrogeological models are needed for this, showing the origins of groundwater, directions of flow and locations of discharge. This approach helps to identify potential sources of pollution and where poor groundwater impacts on receptors, such as springs, supply wells, rivers and wetlands. Water bodies should be homogeneous in nature, but these units are often complex and require further subdivision. Criteria for subdivision include by groundwater flow divides, and shown in this example, 3 groundwater bodies have been delineated based on these groundwater flow divides: 1, 2 and 3. However, the boundaries of groundwater bodies defined in this way may not be static and can move seasonally in response to long-term climate change, changes in recharge, and to the effects of pumping from wells near the boundaries. Boundaries could be based on surface water catchments, which in many cases are closely followed by groundwater flow divides. And this example shows how 2 groundwater bodies could be defined in this way. In this example, a major fault brings impermeable material against an aquifer, restricting groundwater flow to form a boundary. The upper single unconfined aquifer is divided into 2 groundwater bodies, one of which is quite small. But the underlying confined aquifer, the displacement of the fault is not sufficient to impede the groundwater flow. So this is remains and considered as one single water body. The last example is for small shallow aquifers formed by alluvial or glacial fluvial sediments overlying less permeable bedrock. These can form themselves single groundwater bodies. The complexities of aquifers, their vertical dimension in quality, variation and slow movement mean that relatively even small bodies of groundwater are unlikely to be properly represented by one or even a small number of monitoring points. Following the feedback received during the 2017 data drive, it's now possible for arid and semi-arid countries that have extensive groundwater but little or no surface water to report by aquifer-based units rather than the river basin-based reporting basin districts, if they prefer. But these aquifers are often deep, thick, flat-lying with low groundwater gradients. Groundwater resident times are measured in centuries rather than decades. They do not receive significant groundwater recharge under current climatic conditions. They are often heavily exploited already with water quantity management challenges, and they are often well protected against possible quality impacts from activities at the land. And examples of bodies of groundwater which can be characterised by a small number of sampling points. The next few slides looks at selecting suitable sampling points. If there are a good number of sampling options, the general location of monitoring points should be chosen to reflect, as far as possible, the whole groundwater body, especially the source, pathway, receptor, groundwater flow system outlined above. In addition, the network may need to take account of population and land use distribution, with greater densities of monitoring points where agriculture, urban and industrial pressures are most prevalent. Choice may also need to take account of very localised factors around the monitoring point, which could influence groundwater quality and the reliability of sampling. Any monitoring points that are seriously compromised in this way should not be used. The choice of sampling point type also influences the reliability and representativity. Samples of groundwater can be taken from existing wells, supplying water for domestic, municipal, irrigation or industrial uses, from springs or from purpose-built monitoring wells. Each has advantages and disadvantages with respect to practicality, cost and technical aspects. These also need to be understood in the context of the local hydrogeological setting. Many national groundwater quality programs depend entirely, or almost so, on existing supply wells for the cheapness and ease of sampling and the general accessibility for regular visits, providing the monitoring agency has the arrangement to do so. Because these wells are operated frequently, or even more or less continuously, the extracted water is likely to be representative of that in the aquifer. Frequently, the biggest disadvantage of such wells is that there is little or no information available on depths of wells, screened intervals and pumps, water levels, construction materials, and pump discharge rates and times. This lack of metadata can hinder the interpretation and reporting of monitoring results. Some wells may draw shallow, polluted groundwater from the upper part of the aquifer, others from less polluted deeper sections, or even from different aquifers in a layered sequence. Where possible, the monitoring wells should be selected from those for which construction data are available. Boreholes constructed specifically for observation are used in some national programs to improve network coverage where existing pumping wells are absent, and to provide early warning of pollution reaching the groundwater table before it impacts on the deeper supply wells. However, their use requires considerable capital and technical resources for construction and for sampling pumps and for expertise for sampling and including purging the stagnant water. Depth-specific installations, including nested piezometers and multi-level sampling devices, are rarely used in large-scale ambient water quality monitoring programs because of their cost and complexity of installation and sampling. This requires highly trained drilling contractors and sampling technicians, respectively. Their use is largely restricted to monitoring major sources of pollution, such as landfills or industrial plumes, where a well-characterized depth dimension to the quality assessment is essential to observe the growth and spread of a plume. Springs are often undervalued as an option for groundwater quality monitoring. They are cheap and easy to sample without the instability arising from bringing groundwater to the surface, and they are usually accessible for regular visits. Large springs may be representative of substantial groundwater bodies and have reliable discharges even in the dry season. Small seepages with short and shallow flow paths are much less sustained and highly vulnerable to local pollution and should be avoided. In some karstic limestone areas, groundwater movement may be largely restricted to fractures and conduits connected to spring discharges, and therefore springs may be the only realistic monitoring option. As for surface water, sampling frequency for groundwater should take account of hydrological and hydrogeological settings and their reliance on the likely rates of variation in groundwater quality. Historical data or a preliminary survey provide relevant information here. From a monitoring design perspective, it is essential to know whether aquifers are composed of unconsolidated material such as sands and gravels in alluvial formations, or are consolidated formations such as sandstones and limestones. In the former, groundwater moves slowly between the grains, and in the latter, groundwater can move much more quickly in fractures. The absolute minimum for groundwater sampling should be once per year. Higher frequencies of at least twice per year are needed for shallow groundwaters, which are sensitive to seasonal influences from rainfall recharge, pumping and from irrigation, and also those susceptible to urban impacts. Samples should be taken before and after the rainy season and or at the times of high and low groundwater levels. Higher frequencies of at least 4 times per year are needed in karstic limestones. Many aspects of field operations for groundwater are the same as those for surface waters. Health and safety considerations, SOPs, standard operating procedures to ensure data are collected consistently and reliably. Quality assurance and quality control should be designed in from the outset. Field notes are useful to support interpretation and reporting and should include the estimated discharge rate and the length of time the pump has been working, together with observations of conditions around the monitoring location, such as any evidence of very localized pollution impacts. This next section looks at parameter choice for reporting on the indicator and the differences between level 1 and level 2. Level 1 includes the physicochemical measurements of the core parameters, salinity, acidification and nitrogen. These are most commonly reported on using the parameters electrical conductivity, pH and nitrate. But countries can go beyond these basic parameters and report at level 2. Level 2 is optional and unconstrained, and countries can report any additional information they may have. For groundwater, level 2 reporting, the most relevant examples are additional parameters and pathogens. The other examples are more relevant, although not exclusive, for surface waters. The following slides provide some examples of additional parameter groups that could be reported. And here are some examples, but for greater guidance and more detail, please do refer to the companion technical document. So for target setting, knowledge of natural background conditions is essential when setting target values for groundwaters, but also for surface waters. Groundwater quality can be highly variable between aquifers, and higher electrical conductivity values in a certain groundwater body compared to another may not necessarily represent pollution of groundwater, but simply relate to the hydrological and hydrogeological conditions. For EC, for electrical conductivity targets, aquifer or even water body specific targets may be preferable to national targets using a deviation from normal approach rather than setting an absolute target. For nitrate and the associated potential human health impacts, national targets are likely to be appropriate. So in summary, this presentation provides the extra guidance on monitoring and reporting on groundwaters for Indicator 632, but just to reiterate that the greater detail is available in the technical document, which is available on the Indicator 632 support platform. Monitoring groundwater is more complex than surface water monitoring. Aquifers should be identified and groundwater bodies defined using simple conceptual hydrogeological models based on available data. The advantages and disadvantages of using existing supply wells, new monitoring wells or springs for groundwater sampling have been discussed. A proposed framework for parameter groups for groundwater monitoring can be used to identify potential level 2 parameter groups and to support the establishment of improvement of national groundwater quality monitoring. So on this last slide, you just see the link to the Indicator 632 support platform and also the address to the help desk. Thank you very much.